So what I want you to do for lab is problems 1.12. This involves calculating units, working out various problems with units. There's a sheet that has about 10 of these that you need to do. And 1.13 and 14, these involve using Scientific Notebook. There's a video that shows you how to use this software package. This is a very nice software package for doing various types of mathematics, anywhere from algebra through calculus, differential equations. It's quite powerful and it's fairly easy to use. So view the video, learn how to use it, and then work these problems for homework. These problems will also give you some practice plotting up the core functions, calculating the derivatives and the integrals of the core functions. So take the opportunity to brush up on those aspects as well. Now problems 2.1 and 2.2 involve using log transforms to calculate parameters in exponential and power functions. So I put together some videos that will refresh your memory on how to do this. So take a look at the videos. The videos are posted up on YouTube, but there are links to them in Blackboard. So take a look at the links to view those as you feel it would be helpful. The problems that you should do involve this first one is calculating the base flow recession in a stream. And what happens here is that this is the discharge in a stream, the line here, and you can see these pulses. These are storms, but the base flow, or the groundwater component of the stream, is shown here in this dashed line, and it forms a curve that looks like that. Well, that base flow is often fit with an exponential function shown here. And so the task is to determine the parameters in this exponential function. So what I did was to go and select a few points along this curve. I don't show the points, but there are one, two, just a few of them along here. And I started the time at 0. So the first point would be right about there, and I just set that equal to 0. And then I'm using just basically the elapsed time since that point. And these are the discharge. And these are actually from the data shown here. And so you need to do the log transform to calculate what the base flow recession curve, or base flow recession constant, is. And that's A1 and A2. So to do that, you need to use this log transform technique, and it's described in the video, so go ahead and do it. And what you'll need to do is calculate the log of Q here, natural log of Q, and then plot the data up here. You should get a straight line, and you should analyze that straight line to get the parameters. So go through it, plot it up, and show the work. And you should check yourself, because these are the results that you should get. And if you get something else, it could be off by a little bit. It probably will be. I don't expect you to get these exact answers, but it should be close. And you should check your work to verify whatever results you get are reasonable, are in this ballpark. So I give you these results so that you can check and make sure you're okay. But you need to go through and work out the whole problem and show your work, and then hand in the analysis, because I want to see how you go about doing it. And then for problem 2.2, this involves developing a rating curve for a weir. And rating curves relate flow rate to hydraulic head. And what's typically found is that a power function works fairly well. And so I've given you some data. Also, this is actual data from a weir. And you'll go ahead and figure out what the parameters are. So we know that it's a power function, it's given, and so you know from class and from the videos that you need to do a log transform, and that involves taking the natural log of both Q and H and plotting that up and going through the analysis. When you do that, these are the results that you should get. A1 is this value, and it has some kind of peculiar units. And the reason for that is because Q is in CFS, cubic feet per second, and the exponent on H is 2.6. So the units of this term has to be set up so that when we multiply H to the 2.6, we get CFS. So this term has these kind of peculiar units. A2 ends up being about 2.6. And then at a head of 0.5 feet, you should get a flow of about 1.7. So go through, work the problem out, plot it up, fit the line, go through, do your analysis, and because you're doing this by hand, you could get values that are off from this a little bit. But if they're off by a lot, you might reconsider. And work it out, and then hand in the results that show how you go and work through this problem.